Welcome to this coding session. We're going to do something very interesting today, something that I've been curious about for quite a while. And today we're going to implement our first real hashing function in C. And I've picked out one of the simplest hashing functions out there, and that is the so-called djb2 hash. And of course, we're not going to reinvent the wheel and do everything from scratch. The djb2 hash is a well-defined algorithm, and we're going to check that one out today and implement it in C and have some fun and experiment with the code. So, first of all, what is a hash? A hash is basically a function that takes some or any input and scrambles that input and produces an output. So a hash is basically a black box that transforms an input to an output. Now, of course, that black box, that hash, is not just going to do something simple like, for example, multiplying the input by 2. No, that would completely defeat the purpose of a hash. Because what is a hash intended to do? A hash is intended to, or is usually intended to uniquely, to generate a unique output based on the provided input. And the output should be as decoupled from the input as possible. There should be a one-to-one relationship, but if I vary the input a little bit, the resulting hash should be a completely different one. Why is that even important? This is important for making a hash hard to reverse. For example, you have a database and it stores users. For example, you have a website, users can register on that website and, well, they sign up. Now, you don't store the passwords in clear text. First of all, you don't want to know the passwords. You don't need to know the passwords. That is one thing. And also, if your database is hacked, for example, through an SQL injection or some other exploit, then the attacker would only gain access to the password hashes. And if the attacker has access to the password hashes, and the hash function is hard to reverse, meaning that from the output you cannot derive the input, then your hash function achieves its goal. So, and why is it important that slightly varying the input results in a completely different output? Well, this has also something to do with reversibility. Let me just show you something. I hope you can you see this? No, not really. Let me just pull up Paint. So where is it? Imagine you have an XY coordinate system. Okay, everybody knows coordinate systems. This is your y-axis, this is your x-axis, and this right here is the function. The x are the inputs of your function. For example, something like that. And y are the outputs. Now, if you know that, for example, this right here is your input value. Let's say this is the string hello. Okay? Then this right here is the resulting hash value. And if you then calculate the hash for a similar value, let's say the input hello exclamation mark, then this would be the hash value. And this is an example of a bad hashing function because a small change in input results in a small change in the output. You can see I vary the input a bit and I derive the input. I vary the input a bit and the output varies correspondingly. And if you are familiar with a bit of basic maths, you immediately recognize this is something to do with integration derivatives, and you can backtrace the inputs from the output hash. Well, okay, so this is the importance, or this is what a bad hashing function would look like. A good hashing function would look like this. Let's have a look. Let's create a new coordinate system. Let me just fill the axis again, like that. And you have, again, different x values and different y values. Now, let's say this is hello, and this right here is hello exclamation mark. And this hash function would look, or a good hash function would look like this. Maybe that's a bit, that's not very descriptive, but a good hash function would look something like this. There would be no connection between different values. These are distinct values. Right here, maybe the hello with exclamation mark would go into the negative space, whatever, then, and there is no possible connection between different values. There's no intermediate, basically there's no connection between the different values. Okay, that was a lot of text, but I hope you get the basic idea. So, let's try to implement the djb2 hash. It's pretty much the simplest hash which has this property that it is hard, or of course it's reversible nowadays, but it's not easy to reverse. It's only reversible because it is such a simple hash function, and modern computers can calculate or can brute force many results quite fast. Maybe there's even an algorithm for reversing djb2. Wait, let me just look that up. Is djb2 reversible? Oh, okay. Yeah, it can't be easily inverted. And that's the property of a good hash. So it can't be easily inverted. So let's create a new file, djb2.c. Let's include standard.io.h and let's include standard lib. I don't know if I need standard lib. Maybe not. Let's create a main function and save that, and let's just print something out. Hashing or djb2 hash calculating blah 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 blah, and then let's just compile that in over here. Let's compile djb2.c and create an output file, djb2. And of course that doesn't work because I used print instead of printf. So let's change that for printf. And let's compile that, and it worked. And if I execute this binary, then it prints out the string, but without a new line. So let's fix that up. This is always horrible when jumping between different programming languages. You use the print statement from Python, you forget the new line because it's not necessary in other languages. Yeah, okay. So this printf is now working, that is good. Now let's implement the algorithm. So how does it work? Let's just use this website right here. This right here is the djb2 hash algorithm. It starts with an unsigned long hash. The unsigned long is the hash value. Then the hash algorithm takes as input an unsigned character, pointer, string. Okay, it takes in as input a string. And the hash is starting from a number 5381, which is a base value. Then it loops over the individual characters from the string. Then the hash is produced by calculating the hash bit shifted by 5 bits and adding the hash on top of that, and then adding the character from the string as an integer value. Now, what does that bit shift operation mean? Where does that come from? It's not too hard looking at the comments to figure out. This is basically a shorthand and a more efficient way of computation for, or the bit shifting calculation is just a shorthand for multiplying the hash with 33 and adding the character at the end of it. So we could just as well write hash is equal to hash multiplied by 33 plus character. So yeah. Why do we use, or why is 33 used as a number? Is there an explanation? No, there's no explanation for that. Interestingly, the choice of 33 has never been adequately explained. This is also something I find very interesting about many hash functions. So many hash functions contain magic values. Let's just have a look at the implementation of the MD5 hash. This is also interesting. So let's just have a look at that. English Wikipedia. So the MD5 hash algorithm, let's have a look at how it works. Right here, this is the pseudocode. And as you can see, it starts with initial variables right there. And these look like randomly chosen values. And based off those initial variables, some processing and some digesting of the input values is being done. Now, where do these initial variables come from in the MD5 algorithm? This is quite simple. They are not as arbitrarily chosen as you might think. This is just the these are just the numbers 1, 2, 0, 1. Wait, let me just zoom in. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, F, E, D, C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So these are incrementing hexadecimal numbers followed by decrementing hexadecimal numbers. Yeah, so for a good hashing function, or many good hashing functions are actually based off arbitrarily chosen values. There is no mathematical background behind them. And at some point these values were just chosen, and then they were found to be working well. They were just found to be working well. Of course, MD5 was tested in many scientific studies and studies on security and stuff like that. And it was found to be, well, an adequate hash. Full stop. Same thing occurs here. We have two arbitrary numbers on which this hash is based. We have the base hash starting number 5381, and then we have the multiplier 33. They are arbitrarily chosen, and then somehow these values were found to be working well. So I think this is already the algorithm. So the hash is being calculated by multiplying with 33 over and over and over again and adding C. And that is it. So this hash relies heavily on the fact that on the fact that the unsigned long is, for example, 32 or 64 bits. I think it's 64 bits on most operating systems. And if you multiply by 33 over and over and over again, and you do all these bit shifts, then at some point the value is going to overflow, which creates leftover trace values in your hash variable, and then those are multiplied again and C is added on top of that. So this is really a non-linear function. You just cannot figure out the input from that. If a value exits or overflows the available space you have, the available space and the unsigned long you have, then yeah, you get quite random values. Okay, I think it's time to try to implement the hash. So let's let's take as input, as always, an argument count and an argument value array. I think this is the, no, it's not an integer, of course. It's a character pointer, argv. It's an array of character pointers, so it's an array of strings. And then we create a method that returns an unsigned long, and that is the djb2 hash, and it takes as input a character pointer. Should we call it string? Let's just call it input to be a bit more generic. I mean, the input is not necessarily a string. It can be any data you have. And then let's just return 0 for now. And then let's also implement the logic that checks that we have the right amount of arguments. So the arg count must be equal to, I think it must be equal to 2. The first argument is the file name itself, the file name of the binary we're executing itself. And the second argument is the string we're hashing. So let's just do that. Okay, so if the argument count is not 2, then let's print error only one argument is expected. This is a bit confusing for the developer because we're checking if the argument count is 2, but we're printing an error message, only one argument is expected. This is because the user is supplying only one argument. The first argument is the binary file name itself. And let's just make sure that this is working as expected. And let me compile that file, and then let's call it using one argument, hello. Okay, this worked, and if I call it without an argument, we get an error. The error is printed down here. I forgot the new line again. And if I call that with 2 arguments, we get an error again. So this is working properly. Let me just append the new line. And I think it's time to calculate the hash. So I'm going to print the djb2 hash calculating message down here after checking the arguments to indicate that now we're calculating the db2 hash, djb2 hash. And let's then do, I think we can already calculate it. Yeah, so let's just create an unsigned long result that is equal to djb2 called on the first value in the input array. And then we have to do something with the result, and in this video I think it would make sense to just print it for demonstration purposes. So printf resulting, well, let's just say hash value is equal to, and then we print a number, a large integer number. And I'm not sure if we can just use %d because that prints regular integers. So let's just look for printf print unsigned long, just to make sure we use the right printf statement. lu is the correct format for unsigned long. Sounds like, yeah, okay. Okay, so the percentage is the symbol that signifies that we're passing a value here. Then the L stands for long, and U is unsigned. Let's just see if it works in our case. So let's print the results like this. And now if we execute it, the result should be 0 because we are returning 0 here. But let's just check what this compiler warning is. Long. Okay, format #u expects argument of type unsigned integer, but argument 2 has type long unsigned integer. Didn't we just check that this is the correct format for unsigned long? Is this maybe something compiler specific because I'm using a very old compiler, which is just CC? Let's just try it with GCC, which is the GNU CC compiler, which is more modern. Okay, no, we get the same the same error. Probably my CC compiler is internally in the operating system mapped to use the GCC. Okay, so what is wrong with the format? LU is the correct form. Ah, of course. Oh my god. Yeah, excuse the confusion. It must be LU, not UL. So let's compile that like this. Compilation worked. And let's execute it with an input string, for example, hello. And the hash value is 0. That is fine. Then, now it's time to implement the djb2 algorithm. So let's pull up the original page we used for gathering information. And as you remember, we start with a hash base value of 5381. And then we loop over the input string and multiply by 33. And then we add the character. And the base value is an unsigned long as well. So let's just do unsigned long hash 5381. Then we retrieve character C, and then we do a while. While C equals input plus plus. And here we do something. Let me just explain the syntax. The character C here at the beginning of this has no value. Okay, and in the beginning of the while loop, we assign a value that is equal to the input dereferenced. The input is a pointer, and we dereference that pointer, which results in the first character. It's a character pointer, so we receive the first character. The pointer always points to an address in memory. And this is then assigned to C, to the character C. And then after that, the input pointer is incremented. This is something that many people get wrong. The incrementing operator, plus plus, appended at the end of a variable, increments the variable after the operation. Okay. And using this algorithm, we basically just loop over the individual characters in the array. We can just also do a printf C, and then we can print the characters just so you can see it. Why does this not work? Of course, I have to specify that we print the characters like this. And let's go over here. And this doesn't work. Did I do anything wrong? We print a character. Do we have to make sure that this is... Let's just test that. Okay. No. First of all, we have to make sure we have to do this. So we call the increment on the input. What was that? And then we dereference. And then we assign the value to C, and we have to make sure to pass the second argument to the djb2 algorithm. The first one, or the one at index 0, is the file name itself, and that is why you see that djb2 is printed here. This video today is incredibly basic, so in case one of you is more experienced there, sorry. But occasionally I think dealing with foundations is incredibly valuable, and just solidifying what you are able to do. And many people don't, or have an extreme lack of knowledge in the basics. I've encountered this so many times that people don't really, or let's put it like this. People know how to use hashes. People know how to use databases. People know how to whatever, use libraries, but they don't know the foundations. Why is the hash, or why do we use a certain hash in a specific scenario? Why is the djb2 hash not used nowadays? This would be also something interesting to know. Is it maybe too fast, which enables brute forcing for password crackers? Many people don't think about these things, and they just deal with their JavaScript frameworks and libraries. No hate, no front, but, and I mean, I'm totally incapable right now on coding anything meaningful using JavaScript libraries, but oftentimes many people can heavily benefit from just solidifying the basics. And this is one such occasion. So let's compile again and check. And now we are looping over the individual characters of hello. And I think it's quite nice to use this pointer syntax here. And yeah, so the hash will be done very quickly. Let's return, instead of 0, the hash. And then in here we perform the calculation, hash multiplied with 33 plus c. So let's see if that works. Yeah, and this right here is the hash value for input hello. So this works. Now, we could also, instead of multiplying by 33, do this bit shifting operation. We shift 5 bits to the left and then add the hash. Why is this the same thing as multiplying with 33? Well, it's simple. Because bit shifting something by 5 bits to the left is equal to multiplying it with 32. And then we add the hash one more time, so we multiply by 33. Let me just show it to you in Paint. So I just love painting stuff in Paint. Let's imagine you have the following bit pattern in your memory. Let's say 0, 0, 0, 0, 0, 0, 0, 0, 1. So this is the simplest possible 8-bit pattern. Okay? Yeah, okay. Now let's bit shift this by 5. This results in 0, 0, 1, 0, 0, 0, 0, 0. So the 1 moved by, this would be bit shift 1, 2, 3, 4, 5. So we move it to this place, which is this digit right there. Okay? So this is where the 1 now moved. And this is equal to, let's just clarify that this is a bit pattern right there. And this is in, well, what is it called? In decimal numbers. This is equal to 32. Why is this 32? Because the first bit digit would be a 1, the second would be a 2, the third would be a 4, 8, 16, 32. Okay, and this is why we bit shift by 5. And then if we add where is it? If we add the hash one more time, we multiply by 33. And this is one thing that is actually done by many compilers. For example, if I multiply by 33 here, there's a very good chance that the compiler is producing machine code that is already doing the bit shifting. And why is that even necessary? Why doesn't it compile to some multiplication operation? Well, the bit shifting in itself is much faster than explicitly multiplying two numbers. But yeah, that's it. But of course, we could also, I mean, generally, I like the way that the code looks like right now a lot more than doing the bit shifting, because this is more clear. But we could also do hash bit shifted by 5 now that we are experts and understand what's going on here. And then we could add the hash one more time, and this would be the same thing as multiplying by 33. Let's just check if that works as well. And yeah, my point is we can explicitly do the bit shifting here, but there's just a good chance that the compiler is already doing it because nowadays compilers are just optimizing everything. In the past, compilers didn't do that. So the code that a proficient, professional, really capable software engineer was writing was much more performant than the code of a layman or someone who's new to coding, because the proficient coder knew all the shortcuts. But what nowadays is more important is that the code is clear, the code is simple, and the compilers, because the compiler is able to make these optimizations on its own. So you can do whatever you want. You can write multiplied by 33. You can do the bit shifting. It doesn't really matter. I mean, the bit shifting would look a bit cooler, but it doesn't really matter. And if it matters, how much time does it really save you? It saves you a couple of nanoseconds. That might be important if you're doing a server farm and you have millions and millions of accesses per hour or something like that. But it is not important in a personal project. It is not even important if you have, for example, an online business or a trading platform and you have 10,000 users. Still, that bit shifting optimization is not going to break the bank, or it's not going to destroy your business. By the way, these are the kinds of optimizations that colleagues might recommend in code reviews. It doesn't even matter in which language you're doing it. Probably in any language, JavaScript, Java, Python, colleagues will recommend you or tell you you have to use this efficient algorithm to calculate that, whatever. And it's this kind of optimization and the amount of man hours going into the review itself, the code review, someone writing a comment, optimize this, and you having to fix it, and you having to pass all the pipelines, the build pipelines, the test pipelines in a production environment or in a production software, and then having to test everything again. just for a couple of nanoseconds or microseconds of shaved off time. It does not even improve the algorithmic complexity. You can think whatever you want, but I think my opinion is clear on this. Stop nitpicking your colleagues. It doesn't matter if you bit shift, it doesn't matter if you multiply. Yeah, you can suggest such a thing in a code review, but don't insist on it being fixed. It's so unimportant. Okay, this was me going off a tangent, so let's just compile that and see the output of the hello string, and we get a hash value. And let's just try hello exclamation mark, and we get a completely different hash value. And that is what I was talking about earlier. Just a small change in the input, this is just appending a single character, produces a completely different output. Let's just do hello, and then let's place a 1 at the end of this string. And the output, oh, the output of the 1 is actually quite similar. It's very similar. Let's try 2. This is also very, very similar. This might be a weakness of the djb2 algorithm. Let's try 3. Yeah, it seems that here... okay, I know why. I know why that is. That is because the change in the input value is so small, even on character level, 1, or the value 2 is just 1 more as an integer value than the value 1. And this is at the end of the loop. In the very last iteration, it's just added as the plus c right here. And if this plus c is not large enough, it will not overflow the space in the hash. Yeah. So it seems like the djb2, and actually this is quite an interesting discovery here. It really depends on the input. Well, for some input changes, the hash varies a lot, but for others it doesn't. But still, it's not possible, or not straightforwardly possible, to derive the input hello3 from this hash value. So let's keep the hello3, but let's just replace the E with an A. And this should result in a bigger change, because this is one of the first characters being looped over. So the change, the small error, or the small delta change, is going to propagate over during the loop a lot more. So let's just check. So here we have in the hello3 we have 6953583, and in the hello with A we have 695357825. So it seems to vary by the 5th digit. Okay, but I see that the djb2 hash algorithm has its weakness. It's not ideal, but it is probably good enough for most applications. That's quite interesting. Let's just try it with larger sentences. I really like dogs. This is the hash value of that. I hope this has been taken as one input and not just the quote I. And then let's just try I much like dogs. And this creates a bigger change, a much bigger change. So these hash values have nothing to do with each other. So it seems that for big input values, slight changes produce big hash value changes, but for small input values, they don't. It's as simple as that. And that is the nature of the djb2 hash algorithm. That's quite interesting, I think. Yeah, that's very interesting. And I think this is a good time to close this video. If you liked it, if you enjoyed learning something about this hash algorithm, if you enjoyed talking about hashes and the origins and the reasons for some of the things that happen there or that are necessary in the implementation of such hashes, then if you like to do, or if you like to see more of such things, then please leave a like and subscribe, and check out all the other videos on this channel. This is not the only stuff that we do here. So this was more like an experimentation on hashing, which is very, very back-end heavy stuff. We also do a lot of graphics here. I also did some experimenting with Windows API, creating a keylogger, playing around with sounds, and doing some simulations. So we have a lot of different topics covered here, and also suggest more ideas so we can have a look at more interesting stuff in the future. All the videos are available on my Patreon before they are released on YouTube. So if you're interested in having immediate access to videos, then support me there. Have a good rest of the day. Bye.